All right, this is part 2 for this is a screencast for the bellwork from Monday, December the 9th. And I'm now on the back. And I'm looking at 3 different graphs. So this top graph, first of all, you need to recognize that it is a distance versus time graph. And then I'm asking you to describe the motion of the object. Well, I'm noticing that my distance reading is remaining the same the whole time that this object is graphed. So the distance doesn't increase or decrease, which means that the distance stays the same. The object is not moving if the distance reading does not change. So, describe the motion. No movement. How do I know? The distance reading stays the same as time goes by. That's how I know. Okay. So as time goes by, the distance stays the same. Now, what if I was given this? Notice that this particular graph, when you first glance at it, looks similar to this one. They're both straight horizontal lines. But this one's a velocity versus time graph, whereas this one's a distance versus time graph. Okay, I added that one by drawing it, so you guys can do the same thing. Here, it means that the velocity reading is not changing over time, okay? So the velocity value is constant. And what that means this time is that the object is moving, but it's moving at a constant velocity, meaning that it's not accelerating, okay? So horizontal line here, but because this is a distance versus time and this one's a velocity versus time graph, what the graph is telling you is very different in each of those situations. Okay, let's move on to the next graph. All right, next we have the second graph. First of all, generally speaking, if you have a distance versus time graph and the line curves, then I know that it is accelerating, okay? If the line was a nice straight line, I would know that the velocity remained the same because the slope of the line would stay the same. So how do I describe the motion here? I know it's accelerating because how much distance is being covered in a certain amount of time is changing. But let's look at the situation. So at first, at the beginning, the line is fairly steep. And remember that a steep line on a distance versus time graph means that an object is moving pretty fast. But then it gradually gets flatter. Okay, so towards the end it's getting pretty flat. And that's going to indicate less speed, so slowing down. So if it starts fast and gets slow, then that object is slowing down. Okay, yes, it is accelerating because remember, acceleration is either speeding up, slowing down, or changing direction. So yes, this object is accelerating, but what type of acceleration? It's actually slowing down. Okay? All right, let's describe what's going on here in this third graph. First of all, it is a velocity versus time graph. The other two were both distance versus time graphs. So here we've got a velocity versus time graph, and we actually have 2 parts to this particular graph. We've got kind of this, so we have something going on here, and then the object changes the way it's moving and does something different here. Okay? All right, in the orange section, you'll notice that the velocity value is increasing as time goes by. If the velocity value is going up as time goes by, that means that the object is speeding up. Okay? Here, in the yellow section, the velocity value is remaining the same over time, which means that now the object is moving at a constant velocity. Okay? So it speeds up and then moves at a constant velocity. Okay? I'll show you one that's already kind of done so that you can write all this stuff in. Okay, so up here, remember that yes, the object is accelerating, but this acceleration can be considered negative acceleration or deceleration because it is an object that's actually slowing down. So deceleration and negative acceleration are sometimes used to refer to an object that is slowing down, that its speed is decreasing. Okay, and then down here, In the beginning, it's speeding up, and then it's moving at a constant velocity. All right. Down towards the bottom. So you've got a box with a couple of forces acting on it, and I want to know, what is the net force on the box? Well, first of all, please recognize that the 5 kilograms is a mass, so that is not considered part of the force. Okay, that's the mass of the box. I have a 12 Newton force that is acting to the left, and I have a 10 Newton force that is acting to the right. When the forces are pointed in the same direction, then you will add them together. But these two forces are pointing in the opposite direction, so you are going to subtract them. Okay? So what is the net force on the box? Well, that's going to be 12 minus 10, which is 2 newtons. Now, which way is the net force? The net force is going to be in the direction of the larger force. So your net force is going to be to the left because your bigger force is to the left. Okay? What is your acceleration? Your acceleration is going to be found by saying net force divided by mass. Okay? A equals net force. Remember that the net force we found was 2. So 2 divided by 5 kilograms. Okay? And when you do 2 divided by 5 kilograms, you get an answer of 0.4 meters per second squared. Okay? So there you go. Okay, so there's the situation. And then we're going to move on to the final couple of questions. Can an object be moving if the net force on it is 0? And a lot of people like to tell me no. Okay? But listen to the question carefully. Can an object be moving if there's a net force of 0? And the answer to that question is yes. The object can be moving. But since the net force is 0, the object cannot be accelerating. Okay? So the only way it can be moving is if it is moving at a constant velocity, meaning it's not speeding up, it's not slowing down, it's not changing directions. Okay? No acceleration. All right, and then the last question, if forces are equal and opposite, then how do we ever get unbalanced forces? Okay, well, this I had you write in somewhere in lesson 3. Okay, I think it was on the page with the little kangaroo. But if you will remember, like back here with the rocket, I had equal and opposite forces, but one of those forces was acting on the rocket, and that equal and opposite force was acting on something else. This one was acting on the gas. So one is acting on the rocket, one is acting on the gases. They're not both acting on the same object. Okay, so you can still have acceleration. Same thing with the ball down here. Okay, there was a force pulling the ball down towards the earth. And then there was an equal and opposite force of the ball pulling the earth up. Well, one of those forces acts on the ball and the other one acts on the earth. Okay? They are not both acting on the same object. Okay? So here you go. So can an object be moving if the net force on it is 0? Yes. It can be moving at a constant velocity, or meaning constant speed without changing its direction. It cannot be accelerating. Okay? Because acceleration only happens when there's a net force involved. If forces are equal and opposite, how do we get unbalanced forces? Those equal and opposite forces act on different objects. So one force maybe acts on the rocket, the other force acts on the gases. They're not acting on the same thing. Okay? All right, so that should get you up to speed with today's bell work. Make sure that you have it complete. Also, on these last two, I would put an arrow or a star beside each one of them because pretty much I promise I'm going to ask you these 2 questions. Maybe not verbatim, meaning word for word, but I'll pretty much ask you these in some way on the test later this week.